Okay, for the first lecture, we're going to talk about electrostatics and initially just quickly go over atomic structure. So the way I'm going to do these electricity and magnetism lectures is to read through my notes, and then for each block, I'll block these up into smaller blocks with numbered blocks. So what I'm going to do, I want to make sure that I get the main points across. So I'm going to read the notes here. Sometimes I won't have the notes on the sheet and I'll just read them and then discuss it. So I'm not always going to have all the notes that I'm reading out. But in this particular sheet I have the notes. So I'll be reading this and then discussing it, reading that, discussing it, reading that and discussing it. Hopefully then I won't miss many of the important points. So I'll start with number 1 here. The fundamental building blocks of ordinary matter are 3 particles: electrons, positively charged protons, and electrically neutral neutrons. The electron and proton charges have the same magnitude, whose value is the fundamental unit of charge, which is 1.602 times 10 to the minus 19 coulombs. So what I'm saying here is we've got all atoms are composed of protons, neutrons and electrons, and normally they are neutral. There's as many protons as there are electrons, so they're balanced. The protons and electrons are obviously of opposite charge, protons being plus, the electrons being minus, and these neutrons don't contribute to the net charge at all because they're neutral. So that's what that first box is saying. So let's read the second box. In a neutral atom, the number of electrons equals the number of protons in the nucleus. Thus, its net charge is 0, which is more or less what I've just said. So we'll go on to box 3. If one or more electrons are removed, the remaining positively charged structure is called a positive ion. A negative ion is an atom that has gained one or more electrons. This process is known as ionization. So this is quite important. When you have an atom, and say we removed one of these protons, if we remove the proton, we're moving a positive charge away from the atom. So what's happened is then we've got a net negative charge because we're missing a proton. That means this atom is ionized and it's going to be a negative ion. The same argument. If we removed an electron from the atom, then this atom then has more protons than it has electrons, so it's going to be a positive ion. Have I got that right? Yeah, I think so. So here we've got 2 diagrams. We've got this diagram here showing 2 electrons and 1 positive proton, and obviously because of the 2 electrons that's got a net negative charge, so it's called a negative ion. This example here, it's got 2 protons and 1 electron. Obviously that's got a net charge, a net positive charge, so that's known as a positive ion. So that's really, when you hear these terms, positive ion, negative ion, that's what they were talking about. So we'll go on to number 4. All materials consist of billions and trillions of positive and negative charges. I mean, the point I'm getting across here is that all physical objects are made really with atoms and electrons, so obviously there's literally trillions of them in every, in every tiny bit of matter there's billions of these things. So so whenever we refer to the net charge of a body, we only mean the amount of charge plus or minus that is unbalanced. So we're only discussing, when we're talking about net charge here, for example, even if we just pull away 1 from 1 atom, that's the net charge is going to be, it's still going to be a negative ion. If we pulled away an electron, it's still going to be a positive ion. Yeah, so that's really the point here. Just repeat that. Whenever we refer to the net charge of a body, we only mean the amount of charge plus or minus that is unbalanced, which is always a tiny fraction of the total positive or negative charges on the body. Yeah, so the body is composed of trillions of charges, and when we're ionizing something, these are small numbers of electrons that are moving between bodies. So number 5, conservation of charge. The algebraic sum of all electric charges in any closed system is always constant. Charge can be transferred from one body to another, but it cannot be created or destroyed. So conservation of charge is believed to be a universal conservation law. No experimental evidence has shown any violation to this principle. In other words, all the charges in the universe are fixed. From the day the universe began, they're all fixed. So you can't actually destroy charge or actually invent new charge. It's there. It is the elements of the universe are there already. So all we can do is we can break things apart, and we can move charges from one body to another. So we can strip off electrons and put it onto another body, but we can't actually suddenly make electrons, because they're the fundamental particles. So you can't make them and you can't destroy them. All you can do is shift them around, which is quite a deep concept. But that's what we think at the moment. So that's the general idea, and it's what this is suggesting is that there are, they've tried to perform experiments that could negate this, but they've never found anything that has negated that law. So it's put down as a global conservation law. So that's all that's saying, really. All of this is not, this is just fundamental stuff, really, just to get you going. So let's go on to the next sheet. Okay, here we're talking about electrostatics. So here's some examples of moving charges between different bodies. So I've got some, this is supposed to be fur, and here is a nylon or plastic rod. That's neutrally charged at the moment. This is neutrally charged. So if we rub the fur and the plastic rod together, we're going to leave extra electrons on the rod. So electrons are going to come from the fur and they're going to accumulate on the rod. The rod then becomes negatively charged and the fur positively charged. So moving electrons off that, obviously now that's got a net positive charge, and this then has got a net negative charge. So that's how we charge things. So afterwards we're saying here, look, we've got a negatively charged. Notice how the electrons here accumulate all around the surface of the nylon rod. They don't actually go inside, they accumulate on the surface. Electric charge is neither, I've just repeated that from the last page. So here, note, charges only appear on the surfaces and are tiny fractions of all the charges that make up the rod and the fur. Yeah, as I discussed in the last, you're only moving a small amount of charge here when you're doing this. You never move large amounts of charges anyway, and in electrostatic terms, they're always very, very small number of charges. So that's that. Here's the next sheet. Electrical conductors and insulators. So I'll read number 1. It says some materials allow charges to move within them easily. Some materials do not. Conductors permit the passage of charges through them. Materials that do not allow charges to move through them are called insulators. So we call things conductors that allow charge to move through them, and materials that don't allow charge to move through them, we call them insulators. So basically what that's saying is that charges are not going to move between insulators. Although in electrostatic terms they can collect on the surface, they're not going to move from a metal to the metal's not going to transmit electrons through a plastic body and then to earth or to another metal. You need two conductors need to be touching together. In general, metals are good conductors and most non-metals are insulators. So yeah, conductors mostly are metals, and everything else really sort of is an insulator, more or less. So number 3, the fact that metallic elements can form positive ions within solutions shows that their atoms can easily lose one or more of their outer valence electrons. For example, in copper, this losing of electrons by them can then move freely through the metal. In fact, their free electrons are sometimes described as an electron gas. The positive nuclei and other electrons remain fixed in their position and orbits. In an insulator, however, there are no, or at most very few, free electrons. So yeah, that's explaining basically that in metals, what happens is you've got electrons in the outer orbits of their atoms, which are very loosely bound, so they're easy to dislodge, which is what makes metals very good conductors. The fact that their valence electrons are easy to knock out. That's really what makes conductors conduct. So that's that. On to the next one. Okay, I've got some separate notes here, so you're not going to be able to see any notes here. I'm just going to describe charge by induction, because this is really the crux of electrostatics. Yeah, so you can understand this, then you've really got electrostatics. You know, the gist of it, you'll get it with this. So I'm just going to read through my blocks first, and then I'll go in and discuss. So I'm kind of looking at this one first. When we charge a pith ball, and we mean like a little paper ball, yeah, by touching it with a plastic rod that has been rubbed with fur, some of the extra electrons on the plastic are transferred to the pith ball, leaving the plastic with a smaller negative charge. However, we can use a different technique in which the plastic rod can give another body a charge of opposite sign without losing any of its own charge. This process is called charging by induction, and it's been shown in this diagram. So what I'm saying here is this is the plastic rod here, yeah. So what we can do is we can charge up a charge up a plastic rod by rubbing it with fur, and what I've just said there is we don't actually have to transmit any or let any electrons leave the plastic rod, but they can be used to induce charges on other objects. So let's just go through that now. Number 2. So in A, two neutral metal spheres are in contact, each supported in an insulated stand. There's insulated stands here. When we bring a negative charge rod near one of the spheres without actually touching it, as in B here, the free electrons in the metal spheres are repelled by the rod and shift slightly towards the right, away from the rod. The electrons cannot escape from the spheres because the supporting stands and surrounding air are insulators. Thus, excess negative charge must accumulate at the right surface of the right sphere, and a deficiency or negative charge, i.e. net positive charge, arises on the left surface of the left sphere. These excess charges are called induced charges. So here what we're saying is, as we bring this charge, this plastic rod is being charged negatively with electrons here. As we bring it close to these two metal spheres, you can see what's actually happening is the positive charges are being attracted by this. Even though the plastic rod doesn't touch these, the positive charges obviously are going to draw themselves closer because they're being attracted by these negative charges on the plastic rod. And in the same vein, the electrons the electrons are being pushed away because they're feeling a force against them, so they actually they don't attract, they repel, so they're repelling to the farther side here. So you've got this situation. That's what's happened here. So at the moment you're holding this rod close to the two spheres, you're not taking it away, and you've got this imbalance happening. Of course, not all, I'll just read the next section now. No, of course, not all the free electrons are forced over to the surface of the right sphere, because as soon as any induced charge develops, it also exerts forces on the other free electrons. This force is towards the left. It consists of a repulsion by the induced negative charge on the right and a attraction towards the induced positive charge on the left. Thus the system reaches an equilibrium state at each point. The force towards the right, at each point, the force toward the right on an electron due to the charged rod is just balanced by the force towards the left on the electron due to the induced charge. The induced charge remains on the surfaces of the spheres as long as the rod is held nearby. When the rod is removed, the free electrons shift back to the left, and the original neutral condition is restored. So, yeah, what we're saying is, in this situation here, that as much as the charges are being attracted, there are charges in here that are obviously trying to stop that from happening. So everything eventually reaches an equilibrium state. You know, the charge is not going to keep accumulated on this side, because they're going to move. They're going to be next to are the negatives, and the more of these move towards this side, the more they're going to be close to the negative charges that are within the sphere. So eventually you get an equilibrium position, which happens almost instantly actually. So let's read the next box. Now suppose we separate the charge. So now here we're going to separate the spheres slightly. So suppose we separate the spheres slightly as shown in this diagram here. While the plastic rod is near, so we're going to keep the plastic rod near and we're going to separate the two spheres. We are left with two positively charged metal spheres whose charges attract each other. When the two spheres are separated by a great distance, the two charges become uniformly distributed over the spheres. So basically what happens is, as we've got this plastic rod here, when we separate the two spheres, you can see there's accumulation of positive on this side and an accumulation of electrons, negative charge on this side. And then when we pull the rod completely away, we end up with this situation where the positive charges, now it's separated, the positive charges, there's more positive charges on this sphere than there are electrons, and there's more electrons on this sphere than there are positive charges, so they attract each other in this situation here. And then finally, if we pull them away a very long distance, they all will balance out equally, and you'll end up with all the positive charges on this sphere and all negative charges distributed evenly around the surface on that sphere. So you could say there's a sphere that's positively charged and there's a sphere that's negatively charged. But remember, these can be tiny amounts. So even though that's negatively charged and that's positively charged, you know, we're talking about tiny amounts of charge. And that's basically the full idea of charge by induction. There's another way of thinking about charge by induction, and that's when we have not two spheres but a single sphere. So you can do exactly the same here. Now we're going to regard the ground as another sphere, if you like, a huge sphere, if you like. You can think of the ground as a huge sphere. So here we've got the same situation. We've brought up a nylon rod here, which is already negatively charged. I mean, the nylon rod stays negatively charged through all of this demonstration. You know, the charge never comes off the nylon rod, it stays there. The point being that no charges are actually moved between these items. It's just the forces that have caused this to happen. You know, the force of attraction that is felt in this empty vacuum of space that has caused this to happen. So here we just move the negatively charged rod this time just close to a single sphere. Same situation, the positive charges on the sphere are going to be attracted across this vacuum towards this, they want to get towards this negatively charged rod, but of course they can't because there's a space there. And then the same with the electrons. The electrons then are repelled by the same electrons on this, so they'll gather on the other side. Now here's the neat thing. What you can do is you can join this temporarily to ground. Now of course, once you join it to ground, you've got a very large you can think of a very large sphere now, and all of the negative charges will get as far away from this as they can. So obviously they're going to accumulate in the ground. You imagine the Earth as a massive sphere, so they're going to get as far away from that as it can. Now here's the interesting bit. Here we separated the spheres. Now we're going to take that away. We just remove it, and same situation here. We've got this sphere with just a positive charge on it. Same situation here. Now we've got just these positive charges. The negative charges are now in the ground and the earth wire has been removed. So these positive charges, there's a net positive charge on this sphere now, which are being attracted to this nylon rod. When we pull the nylon rod away, a long distance away, those positive charges will distribute themselves evenly over the sphere, and there we have a positively charged sphere. So if you can understand that these two are exact analogies, then you've got a real good understanding of charge by induction and static electricity. That's really the main crux of it.